where was I looking at again? X goes to infinity. So first of all, let's talk about this solution. Tell me what happens to these two terms as x goes to infinity. And by the way, we're going to look only at beta being positive. Actually, sorry, no, we're not. Let's just for a minute, though, consider that. What happens if beta n is positive? So that these are positive numbers. Tell me what happens to that term. Blows up. What are my boundary conditions again? Not blows up. Yeah, exactly. So this is a little bit of a problem. So, right, this is bad. We'll just put that there. We'll leave it. It's not a very mathematical term. But we know there's problems there. What happens to this term? That goes to 0. We like this. It's doing what it's supposed to. It's going to 0. In fact, by the way, it's even better. It's going to 0. It's not 0. Nice, right? And in fact, it tells us something very important, which is we have to throw this solution out. Yes? We'll do that in a minute. Yeah. So negative infinity is going to be the opposite. Okay. But this towards infinity, problems right there. This one behaves like the way we think it's supposed to behave. Now, I made a comment earlier. So if I have a 17th order differential equation, how many conditions do I have to specify? 17. So okay, awesome. You guys are so fast with that. You didn't even like, it took me a while. Okay, this is why I ask you guys the questions like that are hard. Okay, here's the thing. When I go to infinity, I'm saying that I don't have a choice. This thing has to be this. Notice, there's one thing that has to be specified, C2. Wait a minute, if I only specify one thing, that corresponds to a what order differential equation? First order differential equation. So when you go to infinity, it's saying the constraint of this thing going to 0 means that it has to be behaving like it's a first order differential equation. Okay? Well, what first order differential equation? Well, what first order differential equation gives you this? The following does. d dx plus square root beta n psi of n is equal to 0. The most important thing to observe about this is that there's now a relationship between, as I go to infinity, between the function and its derivative. This is going to be my boundary condition. Okay? In particular, remember, I'm not really going to go to infinity. I'm going to go to this thing called L, which is big. I don't know what big means, but what I want to do then is at x equal to L, I want to impose the following. d psi n at L dx is equal to minus square root beta n there's my boundary condition. If the derivative and the function are not related in this way, then it means I have a little bit of this. And if I have a little bit of this, no matter how small that C1 is, by the way, this is a real problem computationally. Do you think you can actually get C1 to be 0 in your computation? You're going to get it to be, at most, 10 to the minus 16. Do you know how big this gets and how fast that gets? To just says 10 to the minus 16, no problem. I'm going to be 10 to the 100. Okay? This thing will dominate. This is a real problem for this. So you've got to be careful. This doesn't ever go away. You can only control it. It's like when they try to stop Jordan. You can only try to contain him. Okay? So our objective then is to contain that and promote this. And that's the condition we're going to impose. You can do the same argument on the other side, at x equals minus L. At x equals minus L, you have something different, because at x, when x goes to minus infinity, then this is the problematic term. You have to get rid of this, because when this goes minus infinity, this thing blows up, whereas minus infinity, that term works fine. So you have a different boundary conditions on the other side, and then you'd just get something like this. So now what we have is a formulation of the full problem, ready to do computation on. We've decided that here's the boundary on the left and right. I have to hit these two boundaries that say they're going to 0. They're not 0, but they're going to 0. So I can solve here. These are the boundary conditions. And we already know what happens in between. So those are the boundary conditions. And here's the equation. So all that work was meant to take care of this statement here. But part of the reason I wanted you to understand this is that sometimes you're not just given simple boundary conditions. On the left is 3, on the right it's 5. You're rarely going to get that in practice, right? Just handed to you like, yeah, it's really simple boundaries. No, it usually comes wrapped up some way like this, and you've got to figure out what that means. You've got to do a little bit of interpretation. Okay? So the proposal is that on Wednesday, we will program this up. Okay? And then, yes?
This assumed that beta was positive?
Yes.
Negative is a whole different thing?
Yes, in fact, I'm going to tell you about that. In fact, you have to assume it's positive, and here's why. Let's go through that argument on Wednesday. So it turns out if you don't assume it's positive, what ends up happening is, yeah, we'll talk about it on Wednesday. How's that? Yeah.
Considering the second order homogeneous differential equation, we can select C1 and C2 in that solution. Why we are not going to say C1 is equal to C0 for
Yes, you could do that on paper. Really super easy. And then if you try to tell your computer this, compute this thing, the computer won't make C1 0 unless you land exactly on the solution. You have two solutions, and generically when you're trying to solve this thing by shooting, when you shoot across, you're going to have a little bit of C1 and a little bit of C2. And you have to figure out how to constrain it. So what you're trying to do, okay, let's back to the rock throwing. You're throwing rocks, and you're trying to hit that. If you even touch this a little bit, you're toast. Okay? That's where we try to manage this away. Right? So how do I throw a rock in such a way that I only hit this? And then so you tell your computer how to do that. That's what we're going to do.
solve that?
No, this is the boundary. OD45 is going to solve this for you. This is what you're marching from negative L to L. When you get to L, you have to ask, where am I? You're not solving anything here. You land. And when you land, you say, okay, where am I? Right? I went over there. I hit the target. This is only at L. Yeah? Okay.